We will now look at few more points. Points to remember. Points to remember about refraction. Points to remember about refraction. We'll just look at few more points. Already we have seen the number of concepts associated with the refraction. We'll add a few more points. As I said, whenever the light ray enters from rarer to denser, it bends towards the normal. So this is how it happens. In this case, this is called as denser medium and this is called as rarer medium. And here we are writing mu2 with reference to mu1. That I am writing as 1 mu2. That is equal to sin I by sin r. Unlike this, if at all, this is a point, the very first point you need to remember. If at all the light ray starts from the denser medium and enters into rarer medium. So this is the case. This is rarer medium and this is denser medium. In this case, this is incidence angle, this is refraction angle. In this case, we are going to write mu1 by mu2. That means 2 mu1 because it is starting from here and ending here. The first medium is going to be denser, second medium is going to be rarer. That means you are getting the first medium refractive index with reference to the second medium. In this case, sin I by sin r. That means if here you are expressing the refractive index of the first medium, that is rarer medium with respect to denser medium, whereas here you are expressing the denser medium with respect to rarer medium. So if at all you want, with reference to this type of orientation, with reference to this type of transition of the ray, then you just reverse this thing. That means 1 mu2 if you want, then reverse the expression, that is going to be sin r by sin I. That means if at all the orientation is changed, instead of rarer to denser, if it moves from denser to rarer, then the reverse the formula which gives the refractive index of second medium always. That means in order to get the refractive index of the denser medium, in case of rarer to denser, use this formula. In case of denser to rarer, use this formula. So this is one point to be remembered. Second point is refractive index depends upon, as I said, wavelength of the light. So when you look at the lights, white light is composed of 7 colors as we know, and you have the range starting from violet to red, Vibgyor we call. So refractive index, lambda of violet is less, lambda of violet is less than lambda of red. Therefore, when you are moving from violet to red, mu violet is greater than mu red. So here violet has more refractive index compared to the red because the wavelength is less in case of violet compared to the red. This is one more point to be remembered. And the third point what you are to look at is, if at all the light ray is traveling x1 distance in mu1 refractive index medium, a medium which is having refractive index mu1, and x2 distance in a medium which is having refractive index mu2. So both are in the same time. Time is same, but definitely the distances traveled will be different because the medium is different. In that case, the formula that holds is mu1 x1 must be equal to mu2 x2. This is the relation that holds good in such cases. So here you need to remember the point, if at all the distance travelled by a light ray in a medium of refractive index mu1 in a time t, and in the same time if it travels x2 distance, if the medium is changed, whose refractive index is mu2, then the relation that holds good is mu1 x1 is equal to mu2 x2. And the same thing you can write in another manner, that is, if at all x is the distance travelled in t1 time in a refractive index of mu1 medium, so this is the distance travelled. If a light ray travels x distance in the time t1 in a medium of refractive index mu1 and it takes t2 time in a medium mu2, the distance is same here. That means the distance travelled, if they travel same distance, but timings are different. Definitely it is different because the refractive indices are different. The media is different. In such case, mu1 t2 is equal to mu1 t1. This is the relation that holds good. So this is one more point you need to remember. So these are all the manipulations from your basic equation, that is mu is equal to C naught by C. And one more point you need to remember here is, if the speed of light is maximum, light is more, then that medium is said to be optically denser, not materialistically, optically denser. It is optically denser. Medium is going to be optically denser, but material wise it is less denser. But here, with reference to the speed of light, with reference to the optical phenomena, it is treated as the denser one. So this is one more point you need to remember. And Snell's law in case of vector notation, Snell's law in vector form. Snell's law in vector form can be written as mu2 by mu1 is equal to sin I by sin r. This is the formula you have. So in order to get this sign in terms of the vector, you can just multiply this with this is an advanced concept in Snell's law. So this you need to look at for the competitive part. So you can just look at mu1 sin I is equal to mu2 sin r, which is nothing but this can be written as mu1 I cross n is equal to mu2 r cross n. So this is how you can represent, and if you can, you just go ahead, but this is an advanced concept. So these are the few additional points that you need to remember in case of refraction.